Hi, my name is Helen. I'm a junior in CC, and I'm a biochemistry and English double major. Right now I'm working at the Owen Lab in Halfmoor. So part of my research is to synthesize these little tiny particles called quantum dots. And the idea is they're little tiny crystals made of semiconductor material. And what's great about them is they emit light. So they actually glow in all different colors depending on their size. These are actually pretty big particles because they're giving off red light, which is longer wavelength. So if I had really tiny nanoparticles, they might be giving off bluish, greenish, sometimes even purplish light. Materials like selenium and cadmium could make a crystal, and that means they have a band gap, just like semiconductor materials. And because of that band gap, when I shine light, like UV light, onto the particles, the electrons will jump up and then back down over the band gap. So basically there's electrons moving and they get excited, and then when the electrons relax, they give off this really beautiful light. So the synthesis happens outside in the hood, and it involves a hot injection and some metal precursors, but after we make them, we take them into this glove box here, which is air-free, and that keeps the quantum dots stable. And what I might do here is, for example, put them out into little vials, and then take them, we actually have a centrifuge inside the glove box. So I can clean the quantum dots inside the glove box, and that means putting them in the centrifuge, spinning them down, redissolving them in different solvents, and then I have cleaner dots without all the gooey stuff that I synthesize them with, and so all the gooey ligands are gone after I clean them. Okay, so we have some type of crystal structure here that alternates. For example, if this was cadmium, the little black ones, and the white ones were selenium, then we'd have what we call, for short, a CAD cell quantum dot. And this is the actual core of the dot, and it's a crystal lattice. And that's usually, let's say, about 2 nanometers in diameter, anywhere from 1 to 4 usually. 4 nanometers is huge. And then what's cool is when we synthesize them, we add like a cadmium precursor and a selenium precursor, but what we need is organic ligands to keep them stable. So this is the actual quantum dot, but what it actually looks like is that there's these huge organic chains sticking off of it, and that's keeping it in solution. So if I wanted to stay floating in an organic solvent, I need to have these ligands, or else they just crash out, and sometimes you see a giant blob of black crashed out dots, and that means your experiment is over. But this is what they ideally look like, and how they stay on is this organic chain might have something like a phosphate, and that has charges, right? The oxygens have negative charges, and that interacts with either the cadmium or the selenium on the surface. And the surface chemistry is actually something that's still totally at the frontiers of this field, and people write their theses on how exactly the ion is attaching to the quantum dot and how these ligands interact with the quantum dot. But the main idea is that we make them in these giant ligands, and then the cleaning process I talked about is stripping some of these ligands off. Because if you want to use the quantum dots for other applications, like today we have quantum dot TVs, or LCD displays, and even what I do is I'm trying to use them for cell imaging. We can't have these giant organic ligands sticking off of the surface. And part of my project is actually cleaning the dots, getting these ligands off, and putting new chains onto the quantum dot, so I can put the quantum dots in, say, water, or some kind of cell media, which is mostly water. I'm usually in the lab 2 or 3 times a week. Maybe more if I count the time I'm just here doing my homework. It's a nice space to work in, but it's something that I've started doing since freshman year, when I saw Professor Owen give a talk about his quantum dots, and that was the one talk that stuck out to us, and we were taking a freshman seminar because everyone else was talking about very detailed organic particles, and here was Professor Owen saying, we make glowy things in our lab. So that caught my eye, and I've worked here since freshman year. So it started out with learning how to make quantum dots, and now I'm trying to do more advanced things, sticking things onto the surface. But it's really made me sure that I do want to be a science major, because you'll sit through organic chemistry and you'll think, I'll never use these ligands ever, what are these chains here? And I actually got to use them. I got to say, let me design my own experiment. How can I put these organic chains onto a little quantum dot? And that's made classes much more interesting. It's made sometimes banal classes like organic chemistry lab feel they're actually developing my techniques. So say we learn how to use a random machine, I actually get to use it here, and that's kind of nice. So it's made classes a lot more meaningful.